Hello, good morning. They call me to introduce our next keynoter, Gilberto Camara, and I asked how many hours I have to introduce his curriculum, but I'll keep it short. Professor Gilberto Camara is internationally recognized for promoting free geospatial data access and free and satellite monitoring of deforestation of Amazonia. He's affiliated with Brazil National Institute of Space Research, INPE, where he was director. Gilberto published 108 peer-reviewed papers, cited over 18,900 times. He was director of the GO Secretariat. He is Doctor honoris causa from the University of Munster and received the William T. Pecora Award. So, we keep it very short introduction of the curriculum. I will pass the word to Gilberto. Have a great presentation.
Thank you very much. Thank you and good morning. Vou só, em português, dizer quão é importante reconhecer o trabalho fantástico da equipe de Belém, da Tatiana, o apoio da Andy e o apoio da toda a equipe, do George. Parabéns. Congratulations. Muy bien, enhorabuena para dos amigos de españoles. So I'll switch to English, but not, you cannot praise enough the courage of these ladies. It was basically geochicas. So the geochicas really deserve praise by the courage. We're lost species. I argued this with Lubia, but let's go to the talk. So when I was invited to give this talk, I said, what I'm going to do, I'm going to do something. And then I said, well, I've been living for 45 years between two worlds. The world of GIScience, where I do my research, and the world of free and open source software, where I do my software. And I kind of reflected, and the first thing came to me is how young you are. So if I say something here, how many of you recognize what this is saying? It was 20 years ago today. How many of you know where this comes from? It was 20 years ago today. Sgt. Pepper's Bottom. So apparently 3 people knew what was 20 years ago. But then I came to the conclusion, and I went back to understand how long has it been since we've had free and open source software. Arguably, you can argue forever, but the landmark for FOSS4G was the first version of GrassGIS, which actually dates back to 40 years ago, 1984. And how long has it been since we have had the term GIScience? Actually, the term GIScience came in 92 by a paper by Mike Goodchild, but arguably the birth of GIScience was when the National Science Foundation of the United States established the National Center for Geographic Information Analysis, which was a major project, and that was 1988. So it's 40, this is 36. So more or less these are contemporaneous, let's say, efforts. And how much of them have interacted? It's interesting to try to span the bridge between these 40 years. So the first point I would like to make is something that there is a saying that scientists build in order to learn and engineers learn in order to build. So there's, for everyone, who are these 2 guys out there? Watson and Crick. And they were building their model, cardboard models, which led, of course, to the DNA. Now, only for the non-Brazilians, what's this plane on this side? Which plane is this? It's the Embraer plane, and of course, I come from the school which led the Embraers. So we had, of course, like I said, in order to build good planes, you have to study a lot. So engineers study in order to build. But my question would be, how much do the GIS FOSS4G engineers have studied the theory? How much is that reflected in the day-to-day of a FOSS4G engineer? And of course, I cannot cover everything. Of course, my talk will be mostly related to my current problem, which is, and then I'm going to phrase it in this following way: how does can GIScience support FOSS4G in the age of big Earth observation data? Which I think it's the major, let's put it this way, it is the major change happening in the FOSS4G world. It's the availability of petabytes of open geospatial data. Okay, so 3 questions. So now in the 40 years now, up to today, which GIScience ideas have actually influenced FOSS4G? Question number 1. Question number 2 is, which FOSS4G tools have enabled better for GIScience? So this is like the scientists building in order to learn, and to build they use tools. And many of these tools, I would say most of these tools, are open source. And the third one, which is more speculative, which GIScience ideas would really be relevant to the future of FOSS4G? So let's start with the first one. And the first one is kind of, in a way, disappointing. It's relevant, but it's disappointing to find out that probably the only major influence of GIScience in FOSS4G is this. How many of you have read this paper? Wow, you should. Know your classics. No, seriously. I'm not joking. Read this paper. This is the key paper on GIScience. Of course, it's not that I'm a good friend of Max, but this is the paper which revolutionized and made it possible to have FOSS4G. Why? Because Max in this paper comes with a simple idea that you can characterize geometrical shapes, which corresponds to the shapes of the objects in the world that we draw on the GI, as point sets. I mean, it's obvious when you read the paper. It was not obvious when you read it. And what are the consequences of that? The 4 intersection paper, as we call it, had actually led Max and then worked at it with Clementini, and they came up with something which was theoretical at that time, the so-called dimension extended 9 intersection model. The difference was, at that moment, OGC was starting. And there was a crucial bit in OGC. How do we avoid what has happened, for example, in, say, Microsoft Office, where people are hooked and constrained by the data? In this case, how do we avoid that companies like Esri or Intergraph would monopolize the market by using proprietary data formats, which was the case at that time? And then, because there was a strong, clear model, this led to the OpenGIS Essentials, simple features, which is a very simple model, but it was essential. I'm going to argue that without this model, we would not have FOSS4G, because there would be no standardization, and there would be no point developing software which would be not working everywhere. And even Esri was forced to adhere to the OGC model. And we have, of course, PostGIS, JTS, RSF, GeoPandas, you have it. And the lesson here is, well, standards need solid theory. The same parallel that we can make if we think about the 1962 paper by Codd on the relational model. It was that paper which presented the relational algebra that made it possible for the SQL industry to happen, to be a multi-billion-dollar industry, because there was a solid model. And I'm going to argue that the same thing happened because we had a solid model, the 9 intersection dimension extended, that made it possible to standardize these operations and made it possible for PostGIS. And without PostGIS, we would not be here. Now, this is, unfortunately, one of the very few contributions that the guys on FOSS4G got from GIScience. They, as we saw here by a show of hands, most of you have not even read the original paper, which you should. But back to it later. Now, on the other side, of course, it's a two-way street. What are, of course, there are more. What are the tools that scientists use to build their models in order to improve knowledge? And I'm going to argue that the most important one by a mile is GDAL. It's fantastic, the work on GDAL, and without GDAL, we'd also not be here. And I'm going to argue that Stack is Matt around? Is he? I haven't seen it. Oh, he's here. Good. Congrats, congrats, congrats. Kudos. Without Stack, the revolution of big Earth data would not be possible to harness. So, two other important. This is like an underestimated contribution, which is the S2 geometry from Google. Those of you who are not familiar to it, you better do it. SF in Ardu, Edza Pebesma does it. And this is a completely different kettle of fish than you use your standard technology suite and transformation suite, because it's regeometry in the sphere. And it makes a huge difference when mapping. And of course, the whole nest, I'm using PyTorch as an example, you could put your favorite machine learning package that people around. Now, so this is, for me as a scientist, on my scientist side, I could not live without these tools and many others. Now, this is the past, or past immediate present. And the question here, what GIScience ideas could be relevant for the future of FOSS4G? So this is the more speculative part of the talk. And let's look at at least part of what has happened while you were doing software on the other side of the fence in the GIScience community. What was happening? A lot of work on spatial analysis. Beginning in '84 and lots of things happening. Lots of works on the field that I have published a bit on it. Lubia likes to say, oh, Gilberto, you never repented publishing ontologies. I mean, you have to publish somewhere, right? But I'm going to argue the ontologies are really useful. But of course, and things like abstract data types for geographical data. I'm going to name these three because, of course, of the limitations of the time. But I'm going to argue that each of these absolutely relevant. And the second two are even more relevant, because the first, what happened in the spatial analysis, is something interesting. Spatial analysis is absolutely essential for, I suppose that all of you know at least a little bit of the tools. Some of these are available in QGIS, for example, so as plugins. But what has happened is something interesting. It's the scientists got fed up, and they decided, and most of the actual FOSS4G work on spatial analysis is actually done by the scientists themselves. So people like Edza Pebesma, Roger Bivant, which has this is the first applied science book. The next one is this is the latest book by Pebesma and Bivant. And of course, the important work by Luc Anseling on the GeoDA, which what happens is they said, okay, the developers are not doing, we're going to do it. So essentially, all the packages, GeoDA and INAR, they're done by scientists. Okay, that's one solution. That does not solve the whole problem, but at least one of the problems is solved. Now, what about what I would say, current state of excitement that happens in the community with this idea of, okay, so if you can do with large language models, with texts, okay, so you say, okay, I can scan the whole Wikipedia, the whole New York Times, I don't care about intellectual property rights, the whole books, lots of the books, and so on, and then I'm going to use a model that harnesses everything and hallucinates a little bit, but it's useful. I mean, those have never used ChatGPT, have obviously, to write parts of a paper, are obviously lying. Okay, I use ChatGPT a lot, and I admit it, on my book, for example, lots of the text is not ChatGPT generated, but when I had something, what is uncertainty? If I am to start a chapter on spatial uncertainty, I say, okay, what's the definition of uncertainty? Then I go to ChatGPT, what is uncertainty? And then I say, okay, this is interest, this is nonsense. Okay. Now, so the success, or whatever, the hype that has been produced with this whole OpenAI, large language models, Meta, whatever, then has led people to say, okay, I'm going to do AI for Earth. So large language models, I'm going to use the paradigm of large language models and come up with AI for Earth. Okay, so the point here is the following. What is the equivalent of a text in an image? Because that's what you talk about. When you have a text on Wikipedia that you scan to be part of your ChatGPT, OpenAI, you say you have a text in Wikipedia that describes, for example, the city of Belém. So when you come up with Belém, you have a description which came from Wikipedia, many sources or whatever, but you have a description. And so what's the equivalent in geospatial data? And people forget that geospatial data is deaf, blind, and dumb. It does not convey, unlike a Wikipedia text, geospatial data does not convey meaning by itself. If you have a curiosity, or some of you are doing, that's how the models are running. You take lots of data and you try to annotate. But it gets worse than that. Segment anything. How many of you have seen segment anything or segment geospatial? Okay. Now we get, okay. So segment anything or segment geospatial, think that the world is a collection of objects to identified in RGB images. So first, they absolutely behead remote sensing. Because the science of remote sensing, of multispectral bands, of texture, resolution, everything, goes out of the window, you guillotine, and you transform everything into RGB chips. And then you think, well, the world has objects, and there's a background and a foreground. That's a basic concept on segment anything. Well, and then you come up with some examples of drone images, high resolution, where you recognize some buildings, which you train. Okay. And then you go, okay, let's use segment anything for real world, like things like we are in Belém for, mapping deforestation in Amazonia. And then, bang! This is what I get from segment anything on an image in Rondônia. Fantastic. Why? Because nature has no foreground and background. Everything matters, in case you have not remembered this. Ask anybody from Belém, and he'll tell you that there's no foreground and background. There's no sense of saying the rivers are more important than the forest, or the wetlands are less important than the deforestation. Everything matters. And segment anything knows nothing about it. Why? Because it has no theory. It does not understand the semantics of the images. So this is, by the way, this is RGB, of course. This is simple algorithm slick, but difference. 10 bands, so remote sensing is alive and well, 23 times series. In other words, this is a 230-dimensional space where you compute the distances between the objects, not in an RGB space, but on a 230-dimensional space. And then, of course, your result is miles better. Not perfect, but miles better. The lesson is, if you don't know your theory, you're going to get busted. So when I say, if you don't know your theory, what am I referring to? No, I'm not going to ask how many of you have read these papers, because I sort of know the answer is. This is the basic paper that started it all, a paper by Ontology and Geographic Kinds by Barry Smith and David Mark, classic paper. This paper is absolutely fantastic. You have to read. If you think you know GIS, if you think you love geospatial information, you owe to yourself to read this paper. Do mountains exist? Absolutely marvelous. Well written to the core by Barry and David. Fantastic. This is very, very good. And then you start thinking about there's more to it than segment anything. And if you're going to go a little bit deeper, if you time, and you should go a bit deeper, because in geospatial information, you are dealing, especially in the age of big Earth observation data, you are dealing a lot with time, although most of you think time does not exist because you just look at maps. You have forgotten about time. When you are confronted with loads of Sentinel-1 and Sentinel data that you connect by stack, time comes right at your face. So read Galton, Fields and Objects in Space-Time and Space-Time. And then comes these two questions, fields and objects, which I could did a career on that, but I just point out what you have to read. And when time is there, comes the notion of events. And again, the paper by Warboy is a critical paper, very important to understand it. So, and yours truly has also published an interesting paper, which I like. I like half of it. Half of it is not good. The first half is very good, the other half is no good. But it's a very interesting paper saying, what's in an image? Because the whole story becomes, remember the question we were asking about what is the equivalent of a Wikipedia text for an AI for Earth? What's there? Because a Wikipedia text reads itself. The city of Belém was founded by the Portuguese, it was da-da-da-da-da-da. You read it. You don't read an image. Furthermore, you don't read a collection of, you have to, and then it becomes the question, what's in an image? What's in an image? It's surprisingly difficult to answer. It's simple to ask the question, because are images capturing continuous variation of phenomena, we call them fields, or are they capturing sets of objects? In which case, this is the RLC, this is the Landsat series from USGS, where you can see the encroaching of RLC due to salinization. And again, you could say, well, where is the RLC? Is the RLC there the same as here? Or are we talking about an continuous extension of land, a continuous extension of water, and these continuous extensions change over time? The question has no clear answer. The answer is it depends on what you're doing with it. So the idea here is there's more to it than an RGB image, an RGB photo. There's things that happen in the world. Like we say, objects exist, events occur. So for example, we like to say that Mount Etna is an object, but then you have to first read the paper on do mountains exist? Surprisingly difficult answer. But of course we know there's something like an eruption. An eruption is not the same cognitive sense, semantic sense as a mountain. An eruption is something that happens. Mount Etna is something that exists. And then you start thinking, so what I thought it would be simple to think that I can very simply have the equivalent of Wikipedia in my large language model, think again. Read the classics first. So some examples, for example, one object could be a forest, an event could be deforestation, an area could be a crop area, an event would be sowing, senescence, and the bare soil. An object could be an ice shelf, an event could be the breakup of an ice shelf, and so on. So things happen to objects in the world. And it's not anything obvious to capture. The images don't talk. So how, these images are not Wikipedia pages that talk. How do you find out what's happening? What has happened? How do you find out what is changing? So it's not a question of chips. It's a question of understanding the whole process of coming from what we call the external reality. You think things exist, you observe them. And then what you observe, our eyes observe, are actually continuous variations. And it's up to us, our algorithms, our meta, to define, okay, I'm now calling this mount here Mount Cotopaxi, which is absolutely convention. If you some of you deal with digital terrain models, TINs, there's no objects in digital terrain models. There's just terrain variation. So here is pretty conventional that I call objects and I say, well, and then it exploded in August 2015. So these concepts that have to do with our observations, which are the images. So the images sit here. They are not a collection of texts and events. It's up to us to make them work. So it's not simple to translate and to build a large language model out of raw images. So time matters, space matters. Starting with the spatial resolution. When you have, for example, a weather prediction model at 5-kilometer resolution, there's no sense in talking about individual running segment anything on that and trying to find individual objects. On the other hand, if you have a drone image of 30 centimeters, you may be interested in finding objects in the image. So what you want to find in the image will depend on the spatial resolution of your data. And what are you doing with this data? Are you using for natural change? Or are you using for identifying, for example, cars in a city or buildings, or doing mapping, automating, for example, updating your cadastre in a city? Well, it depends on the spatial resolution. And also depends whether your images are infinitely, you have one image, or you have a seasonal image, or you have a daily image. What you actually view, the things you can view, for example, in a single image with 1 meter resolution, yes, you may identify objects in the background. In this case, you may try segment anything, although segment anything simply has killed remote sensing, but never mind, you build one more of those, that have nailed remote sensing to the wall. But of course, if you are now having numerical weather forecasting with 1 day or 30-minute resolution, you are here very much on the realm of having fields and events like floods, for example. So what information you want to obtain depends a lot on the data you have, the resolution, the bands, the time. And this is not, I'm not making this up now. This has been a huge amount of discussion on GIScience. And unfortunately, this community, FOSS4G, has sort of been in parallel with this community. And now, of course it worked. Why did it work? Because for a long time, all that matters was doing things with vectors, PostGIS, QGIS. You're automating cadastre, you're simply saving money from the local administration, from health. It's fine. So you're basically replacing ESRI. Your fight is, I'm going to replace ESRI, commercial software, with something equivalent. Fair enough. Now that you have a new world coming with lots of data, Esri doesn't have a solution for big Earth observation data. So who are you fighting with? You're fighting with yourself. So if you don't know the theory, how can you get it right? So all of this has been discussed before. It's not new. And of course, one thing that our community, at least my left arm, the FOSS4G arm, is yet to understand what is the impact of time. What does time bring you? So this is a time series of 1 point. So it's not an object, it's a point, pixel, a location, in an image. And for those of you who are not familiar, this is an NDVI, which is a proxy for the greenness of an image, proxy. And of course, you get you get high NDVI from 2000 to 2003, but this was a forest. And then you have a clear break, which is associated with deforestation. And then for about 10 years, you have a signal that oscillates between low and high, but with a great, let's say, expansion. So it becomes high for about 6 months and low for about 6 months, which is typical for a pasture. And then the signal changes again. And it changes again because it now has peaks, very well-defined peaks, of areas with very low NDVI, and suddenly the area becomes, the same pixel, becomes very high NDVI. And then sometimes it has 1 peak, sometimes it has 2 peaks. Well, this is typical from agriculture, and in this case, multi-crop agriculture, soy with cotton, soy with corn. And then you have the story of a pixel. Is this an object? What are we seeing? We're not seeing an object. There's no sense of talking about a pixel being an object. It's just an information that is there on the image. So the question becomes, information is there. You know it's because it's there. How do you take it out from the fact that it exists? To that, you have to understand, okay, things change. I do need, if I want to capture change, I do need to codify the events that might have happened here. Now remember, the place, the location didn't change. What happened to that place has changed. So this is real-life example. This is the average of a whole area in Rondônia. Rondônia is about 600,000 kilometers, so all the pixels in Rondônia, some of them have a signature of a burned area. So just look at the blue one, which is the NDVI. You can see that it starts in the year with a high NDVI and simply falls down. The second down is a forest, where you can see that it's more or less high during the whole year, which is short. You have another one which has fallen down, but not so much as this one. And there's another indicator here, the NBR, which is the burn ratio, which goes very low in this case, but doesn't go very low in this case. And this is another case where there has been a cut, but not so much in the regeneration. So it had been 2 events. One event of the cut, one event was the regeneration. So we're now talking about events. We're talking about events guiding the selection of samples. Okay, so what? Oh, very good. So what? What you get out of that? Well, you get out of it something very concrete. It's the first time that we have in Brazil, Brazilians know this, visual interpretation system which is used to map deforestation in Amazonia, called PRODES. Our friends from IBAMA, George, know it very well. Up to very recently, there was no system that had been published, I'm not saying it does not exist, but it's not published in the literature, which achieved the same kind of quality as the visual interpretation, which is of course hard. But with this event-based approach, we get F1 scores of clear cuts on the same range of quality as the PRODES. It took a huge amount of work, years of work. It's not like something you do in a week. Thinking about what events are there, thinking about how to map these events, how to characterize them, think about how to represent them into signatures of time and how to separate them. Now, almost finished, but so many of you who work with Earth observation data, I don't know how many of you have worked in one way or another with Earth observation data, or just, okay, about half of you. And those of you who have not may work, because I'm saying this is the hot topic on free open, I mean, of course, supporting the use of free and open source vector GIS will never go out, because it's something which is eternal. So eternal things do not age. But as in terms of novelty, in terms of what we do, this is where things have changed more in the last 5 years, 10 years. Big satellite data organized as data cubes and machine learning. That's the paradigm, and then people say, okay, let me write a Python script using whatever, and then, of course, our community, like my right arm, is also very much something that you don't do, and I have to praise your community. That's why I'm very proud to be here, because the research community is failing strongly in sharing. And once I was a keynote speaker at IGARS, one of the prime conferences, and there was nothing to do. It was very hot. I was alone. My wife was not with me, so I had nothing to do. So I looked at every one of the 1,320 papers and found out, everyone, I read every paper. So I found out that only 35 of them published in any way, shape, or form something which shareable. Go to remote sensing journal. Count how many papers in remote sensing share their code. This is ludicrous. So, and people do anything and publish anything. Of course, the community of FOSS4G knows better that without sharing, you don't make progress. But still, there is one thing. As the gringos say, there's an elephant in the room. In this case, literally an elephant. Brazil has a savanna, Africa has a savanna. We were once together. We split the continents, but the edaphic conditions of the Brazilian savanna are very similar to the African savanna, but we have their elephants there, and our elephants have been killed. It's a long story. But in any case, there's an elephant in the room. What does it mean? It means, back to the ontologies, so we talked about fields, talk about events, talk about observations, and let me wrap up in talking about the whole issue of characterizing the world in terms of classes. That's the word, essentially what ontology means. Ontology means description of what is there. And then you say, okay, what is there? So ontology gives to you, not that you're going to start doing ontologies, it's the mindset that matters. What is there? What is there? So you have a Cerrado in Brazil, covers 2 million square kilometers, a latitude from 5 to 25 south, 5 north, 25, huge latitudinal range. Very different occupations, open Cerrado, Cerrado stricto sensu, Serra down. So if you do not go back, if you just start doing algorithms without understanding the ecology, you're going to fail. Sometimes it's easy to fail when you have a lot of money. Let me give you an example. No, serious. I hope you're going to agree with me when I say, if you are looking at preserving the planet, you have to be very careful in separating what is the natural state of the world, or at least the least preserved state of the world, and what is the state of the world that has been, say, changed by human action. In our case, there's a natural savanna which has a natural biodiversity. It's not a forest, but it's savanna, still biodiverse. And the pasture in the same area, competing for resources, which has been significantly depleting the natural vegetation. I know my friends in Ibama, Georgia, is here thinking about Pio de Cerrado, and this is a fight we fight every day. Now, George, look at what money can do for you. Okay, so the European Commission puts satellites, and then I'm gonna pay a lot of people to do a world cover map. Have you seen this map, George? Okay, the world cover map, 10-meter resolution 2020. Fantastic work. Yes, it is. Look at this. This is the world cover map from ESA. This is the map that we did with time series in Brazil. This is my PhD student thesis. What is yellowish here is something, a catch for a word. This is why ontologies matter, because words matter. So when I say that images don't talk, we talk for them. So how do we talk for them? We give words the power to represent the world. And we go looking for these representations of these worlds in an image. So these guys from the European Commission, or hired by the European Commission, defined something called grasslands. So anything which is not a big tree, it has something this height, is a grassland. Look at, this is the yellowish bar. Now look at the map down, and you see now the shades of green. The shades of green are the different types of natural vegetation. Those I showed, the Cerrado. And then the yellow, more or less pastelized color here, is the actual pasture, the actual man-made pasture. So what is an indistinct description of the world in the ESA map becomes a clear distinction between what is natural and what is man-made in a map that the people who did it know their ontology. So the guys don't know what they're talking about, so they took so that's going back to my early example. We, images don't talk, we put names on them. And if we put the wrong names, if we say there's grassland there, there's no way you're going to find the difference between what is natural, what is man-made. So, George, you agree with me, this map is useless for you, right? Completely useless. The environment here, George works at the Environmental Protection Agency. What kind of information does this map convey to him? Which areas he has to protect? So, again, ontologies matter. And finally, a little bit about how many of you consider yourselves lovers or experts or favorable to object-oriented programming. Just 3? 4? Okay. Well, I suppose most of you, when you do your work, you do in Python, right? Okay. Now, how many of you have actually studied or worked with functional programming? Oh, okay, good. So you would have a challenge for you, which you don't have to say today, which is the following. How many lines of code does your API need to classify 200 million hectares? Those who know the answer, keep quiet. You can have a range from 0 to 10, from 10 to 50, from 50 to 100, or from more than 100. Guesses? Any guess? Please, take a guess. 200. Okay, good. No, lines of code. You are coding in Python. You have to develop a model that does the API. So it's lines of code. You are now back to your computer. Okay. Well, surprising, if you would be surprised, perhaps, to find out that this issue has been subject to research by the GIScience community. And the research has gone into trying to understand how to break the system in pieces. So the essential idea of the research was the thing to do is, okay, what do I have to do to achieve the classification of 200 million hectares? Well, I have to obtain the data, which is in a collection. I use Stack for that. I have to put this analysis-ready data in the cloud. I have to build a data cube out of it. Okay. On the other hand, I have to collect some training data. I have to do some quality control on this training data. But then I have to train the data set with a machine learning method. Okay, this blocks. And then I have to classify the data using the data cube and the trained data set. Then I have to perhaps to do a smoothing to clean out the outliers. And finally, I obtain my map. So this kind of abstract thinking says these are functions. Each step is a function. And if you go back many years, my good friend Andrew Frank has a paper who says exactly this. How do you think functionally when doing GIS work? It's a classical paper by Andrew. Very good. Puts your mind in the right direction. And there is also a very interesting paper which I think you have to read. It's a paper by Werner, which is core concepts of spatial information from transdisciplinary research. You owe yourself to read this paper. You need to read it. It opens your mind. And of course, yours truly could not fail to be here. There's a paper by Mai, Max, and others, and Lubia, of course, which is sitting right in front of us, called Fields as a Generic Data Type for Big Spatial Data. The same idea, the idea that you abstract classes and functions on these classes. So, leading all this theory, but when you sit, you say, okay, going back to that. Okay, I've conceptualized my work, my workflow. Now I need to come up with types and functions. So I need to define whatever a type, I'm going to call a data cube, and I'm going to say, I'm going to extract positions out of the data cube and call them samples. And I'm going to apply a function to the data cube and get another data cube, for example, putting an NDVI. I'm going to train the samples with an algorithm and get a model. I'm going to classify the data cube with this model and get a probability map. I'm going to smooth this probability map and with some function, and I get another probability map without the outliers. Then I label the probability map. If you think this way, the whole conundrum whether, for example, the algorithm is a random forest or is a temporal convolutional neural network is useless. You're not these are details on the abstract concept. So if you now have the abstractions, then you can finally respond to the question, how many lines of code do you need to classify 200 million hectares? And the answer is 6. 5 in this case, but I could add one more. 5 code. Obtain a cube, in this case from the Brazil data cube, get the samples of the Cerrado, train this with a temporal CNN model, train, classify to get a probability map, label the probability map. And all the rest are details. What happens in the train function is not the problem of the user. 5, 6, most. Now compare, try to do it. Your favorite machine learning method. How many lines of code would you need? And what's happening? It's not that you're a bad programmer. Not at all. It's happening because you have not read the classics. Because you're doing without the basic stuff which I asked again and again and again. Scientists build in order to learn. I use GDAL a lot, Stack a lot, to learn things. Now, are our engineers doing their homework, learning, studying, knowing the classics? Like I said, for a while, it didn't matter. because the work had been, heavy lifting had been done for you, where you have the simple feature in the OGC, which started with Max Sigenhofer's papers in '91, and okay, life was good. Now you have something that challenges. There's no longer Esri to beat, because Esri is not even in this game. So are you fighting? When you fight with yourself, you sit at the computer, and you have nothing else than your good sense, if you don't know the theory. But it's hard doing things alone. It's hard doing things when you have no guidance. So please, study your classics. Thank you very much.